All right, let's talk about exercises involving the binomial distribution. By the way, I have a fan going on my laptop to help cool it down. Hopefully that's not being picked up too much in my mic, but I guess we'll see what happens and play it by ear in future videos, depending on how it goes. So anyways, let's just define it. The probability of observing k successes among n trials with success probability p, i.e. the probability of each success occurring is p. This is given by combination n, let's see here, n choose k times p to the k times 1 minus p to n minus k, where we have this combination formula n choose k is equal to n factorial over k factorial for n minus k factorial. And these are just the formulas. And of course, it's a good idea to memorize these. If you do enough exercises, you'll probably just memorize them by accident because of just repetition. However, it's really good, especially if you're in like a high pressure scenario. Well, I suppose that if you're interviewing someone, I suppose you could just ask for the formula, and if they're generally it's better with these sort of technical interviews to sort of think of it as more of a group problem solving session than as a exam. Because really the interviewers want to see how well you work on problems, but also how well you work on problems with other people, because in these positions you'll presumably be working on problems with other people. So anyways, if you forget them, I assume it's not the end of the world if you ask for the formulas, but it's also good to understand the formulas well enough, or understand the underlying situations well enough that you can rederive these formulas if you absolutely need to. So let's think about how we could derive these. So for the combination formula for n choose k, so n choose k, what this is it's essentially it describes the number of ways of choosing k items out of a collection of n items in which the order you choose them does not matter. And so why would this formula apply to this? So one thing that you could do is you could think of it as you have a number of items. You have item 1, item 2, all the way up through item k. And let's say you choose this item, you don't choose this item. Let's give us a few more items here. Let's say you choose this item, you choose this item, you don't choose this item, you choose this item, you don't choose this item, and then eventually what you have at the end is you've not chosen n minus k items, and you've chosen k items, because we're trying to figure out the probability of or the number of ways of choosing k items out of n. So what we've done here is we've sort of constructed a sequence of C1 through CK and NC1 through NC n minus K. And so if we think about how many different ways can we mix around these C's and these NC's so that we get different ways of assigning different items I1 through IN, assigning different items to being chosen versus not chosen. Well, if we think of each of these labels as being distinct in this lower part, each C1 through CK is distinct, each NC1 through NC n minus K is distinct, then there are n factorial ways of arranging these, because C1 can go in any of the n spots, C2 can go in any of the remaining n minus 1 spots, C3 can go in any of the remaining n minus 2 spots, etc., etc. And you get n factorial combinations. However, we don't care about reorderings. It doesn't matter if we, so what we could have done is, with this way that I've written everything out here, we could have C2 and C1 switched, and it doesn't change the fact that I1 and I2 are both chosen. So what we need to do is we need to divide by the number of ways of rearranging the C's and the number of ways of rearranging the NC's. And the number of ways of rearranging the C's is k factorial, because there are k of them, and so C1 could go in any of these k locations, C2 can go in any of the remaining k minus 1 locations, etc., etc. And so that's how you get k factorial different orderings of the C's. And similarly, because there's n minus k NC's, there are n minus k factorial ways of reordering them. And so by that logic, you can rederive this formula that n choose k is n factorial over k factorial times n minus k factorial. All right, but then how about this binomial distribution here? So the way that we can think about this is we want the probability of observing k successes among n trials, and the probability of success is p. So let's first consider the scenario in which you have k successes followed by n minus k failures. What is the probability of this event occurring? So the first event is a success, which is probability p, and then the second the second trial succeeds, so that's probability p. And so because we have p successes in a row, we can sort of think like this. If this is the first trial, this is the second trial, and this is the kth trial. Here, I'll put the trial labels down below. 1, 2, all the way up to k. So the first k trials, all succeeding, has probability p. You multiply p by itself k times. So that's going to be p to the k. Then for the remaining trials, from k plus 1 all the way up to the end, which is n, we're going to have a failure. And if the probability of success is p, then the probability of failure is 1 minus p. So we have this. And so we have k successes, so that's p to the k, times we have n. Let's see, if we go from k plus 1 all the way up to n, then that's just like having all of the n and then subtracting the first k. So that's n minus k. No. So we have n minus k copies of 1 minus p. So this is 1 minus p to the power of n minus k. So that's how we get to the p. This is how we derive the p to the k times 1 minus p to the n minus k. Now to get the combination, this probability that we've written out here is just the probability of getting k successes and then n minus k failures. However, all we care about is the probability of observing k successes at all among n trials. So we don't care which order the k's occur in. We don't care if they all occur at the beginning or if they all occur at the end or anything else. And so we need to multiply this probability by every way that we can mix around the successes and the failures. But again, the order doesn't matter. Like each of these successes are not distinguished from each other. A success is a success whether, and its status as a success is not impacted by where it occurs in the sequence. And so because we're reordering these things and because we're mixing the successes and the failures in such a way that the orders do not matter, we need to multiply by n choose k. And so that's exactly where the n choose k comes from. And so that's how we get this final formula for the binomial distribution. So if you forget about the formula, this is one way to remember it. Hopefully you won't have to deal with that during an interview, but it's nice to have that as a backup in case you get really nervous and you start to blank on things. And it also just shows that you have a better understanding of the underlying principles that go into deriving the binomial distribution. All right, so now that we've seen the binomial distribution, let's just show an example of how you would apply it. And generally with these, it's really straightforward. Once the hardest part is knowing the formula, and once you recognize that you need to apply the formula, you just plug in the numbers. So let's say you roll 5 dice. What is the probability of rolling 3 ones? All right. So the solution. So if you do enough of these problems, you'll immediately recognize this as a binomial distribution problem. So we're rolling 5 dice, so that's the number of trials that we have. The probability of rolling 3 ones, so we want 3 successes. Rolling a 1 is considered a success, and we want 3 of them. So k equals 3, and then each success is rolling a 1, and there's a 1 in 6 chance of rolling a 1, so we've got this. All right, so then our answer is going to be 5 choose 3 times 1/6 to the 3 times 1 minus 1/6 to the 5 minus 3. And then we just sort of write this out. So this is 5 factorial over 3 factorial times 2 factorial. Then we have 1/6 to the third, 5/6 squared. If you write out this 5 factorial, so this is 5 times 4 times 3 times 2. Then this is 3 times 2 times 2. I ignore the ones because they don't really matter. So we got this here with 2. Still got these. So this is going to be 10 times 1/6 to the third, 5/6 squared. And there's if you at this point, I don't think they're really going to want you to like do the numbers and everything. I mean, if you really need to, I suppose it's possible. But this is really more, at this point, you just plug it into a calculator. If you were to do that, you would get, let's see here, 125 over 3888. Let's see here, 5 squared is 25, so it's 250. So basically, you would be able to reduce this fraction. You'd be able to reduce the numerator from 250 to 125, and then the denominator from whatever 2 times 3888 is down to 3888. But of course, like, that's something that I think would be pretty weird to see. To do like a lot of like numerical calculations in an interview. But anyways, so this comes out to 0.032 approximately. So this is about like a little over 3% chance of this happening. So yeah, once we saw to use the binomial distribution, there wasn't really much else interesting to do in the problem. It was just plugging in numbers and doing calculations and stuff, just sort of more tedious, routine stuff. That's not, I feel like that's not where the real interest in this problem is. The real interest in this problem is seeing the problem statement, recognizing that this is a binomial distribution problem, and knowing the binomial distribution and remembering what it is so that you can apply it. But yeah, these are, seems like a question that can come up in an interview, and so it's good to know the binomial distribution and know it well enough that you can apply it whenever it comes up. So if you get an exercise like this is how you would do it. Basically just know the binomial distribution.